So I'm just looking in the chat. In the beginning, many people are not very used to it. So maybe let me first start with a very general question. So my question is respect to the, let's say, this static approach of homogenization versus dynamical one. In very often we just try to retrieve the elastic tensor, and from my experience doing this, let's say, dynamical experiments, but basically computing the dispersion relation is much easier from the boundary conditions than taking a microstructure and imposing the sometimes very funny relations on the different surfaces in order to solve the homogenized problem. And I was just wondering, is there anything that actually one can not actually get from the dispersions that you would basically use in your approach that would be more convenient than using the standard dispersion relations?
Well, if typically at the second, let me go back to the example for the second order homogenized equation that I have introduced. You see here that the dispersion relation gives you a relation that are a combination of the effective parameters. So of course, this is an observable that you can have access to using some experiments, but you don't have access to fully the effective parameters and the effective tensors. Maybe that is enough for a given application, but if you really want to characterize the complete model, effective model at the second order, you need to perform the full asymptotic analysis and the computation of all of the cell problems. So, okay. So I would say that's doing this. The model is complete. Whether you need it or not, that maybe is another question.
I get it. It's just that, I mean, if you just take one unit cell. Let's say the one you were showing, I think it was slide 23. You have a cubic symmetry, and yeah, this one. If we just assume that it's a 2D yes. structure, so then from the symmetry aspect, you know how many effective parameters you would get for such structure. Mm-hmm. So then if you look from the dispersion relation aspect, you know basically along which directions it would be the most convenient to try to retrieve this effective parameters.
Yes.
And is there a general procedure for that in this quasi-static computations? If I say that I'm in the, let's say, in the most anisotropic case of in mechanics, so nothing, it's not cubic, it's this the forgot the name for the triclinical for the most general one. And then I could have some chiral structure inside. How would you approach that problem?
So you mean so to identify the macroscopic properties from experimental data?
Not only from the experimental, but is in your case. I mean, I'm just have trouble to identify how you would implement in general these boundary conditions on your unit cell in this static case.
But by implement, you mean like in practice, or because so here numerically you have a description of the microstructure, and the Fourier-based approach directly gives you a way to handle the periodic boundary conditions. So you can compute the cell problems. You have access to all of the cell functions, and then you can compute the effective parameters. So the power of this Fourier-based approach is that it gives you directly a way to handle periodic boundary conditions.
Okay, maybe that was my misunderstanding from the.
Yeah, and usually doing finite elements, it's relatively standard as well. But since the solution you're looking for is periodic, it's very natural to expand it into the Fourier basis.
Okay. Thanks. Do we have more questions from the audience? Looks like that. No. And let me just continue on this approach. I think it was among slide 23, but maybe a bit further when you said that you yeah, this one. So computation of 12 scalar static cell problem. So then again, this is it's well known. Maybe it's not for me, but the equation that the conditions that you will use to get this 12 scalar static problem.
The question is how to quantify the effects of a perturbation, of a small perturbation in the microstructure on an effective properties. So typically, if I have the microstructure in gray here, a reference microstructure in gray, and then you suddenly introduce a small perturbation in blue. Of course, this perturbation is periodic. How does that change each of the effective parameters? And so that's a work that has been done in a previous paper. Typically, computing the corresponding topological derivative has to be achieved through some solution of the static cell problems. So that's also an asymptotic analysis, but I mean the analysis is done. Now we just use the formula basically.
Okay. Audience, is there any unclear aspect for you? Everyone looks shy. So let me ask a last question regarding this topological optimization that I think it's in the slide after, if I remember properly. So in general, do you how basically, I mean, in this topological optimization, in very often when I follow, for example, the work for Sigmund, it's more or less like I mean, it's a random stuff that you introduce inside. But do you have any additional algorithm that you on the continuity on the one phase compared to the other? How do you optimize this as well, the symmetry aspect inside of one of the unit cell, if this would be, for example, a one unit cell of a material?
So here, basically, at each point of the discretization, each point is independent. All points are independent of one another. The microstructure that will be generated is periodic because we used the underlying FFT-based methods. So periodicity is directly encapsulated into the forward solution methods. Of course, there are several local minima to the cost functional. I mean, there is no uniqueness of the microstructure for a given cost functional. So we reach one local minima using this gradient-based algorithm. But we can introduce some constraints on the microstructure. So typically on the next slide, you see that we've started from a random microstructure, but that had some symmetry. So 1/8 of the structure is symmetric. So we directly encapsulate the constraints into the initialization of the algorithm. That's the idea. So you can add some constraints. Some of them are relatively easy to handle, such as symmetry. Some can be more involved actually. So.
And just to finish on that aspect, do you have any possibility, for example, this slide actually is very well, it's a good example, because in the previous one, when you study this small perturbation, you could probably see that in some cases, this perturbation has almost no influence on the effective property. And can you, in a way, implement this as a double problem, the topological optimization that I see on this slide, combined with the fact that you would know that for some geometry, this small perturbation would not have any influence, just to minimize the number of iteration?
Yes, it's a good point because what tells us the asymptotic expansion of the cost functional is that in some cases the effect of the modification of the microstructure is very small, very tiny, and in some cases it's very hard to move from one initialization to a microstructure that looks to us satisfying in some sense. But that's the effect of the gradients. I mean, that's how things are. So our belief, it's like here we are doing optimization of microstructure in the linear case, and in the case where each phases are relatively comparable to one another. Okay. And if you want to have stronger effects, you need to have resonances, and typically introduce high contrast in the microstructure so that this tiny influence of a perturbation will be much stronger, in fact. But that's future work, basically.
Okay, thanks. And if I look in the chat, there is a question from Manoj. How would this approach compare to 3D cells with 3D periodic inclusion, to be specific?
We have only done to the example, to the computations, but there are essentially nothing that changes in 3D. For the FFT algorithm, you can. It's straightforward to compute a FFT in 1D to 2D to 3D. So it will be the computer that will work more heavily. And from the for the topological optimization parts, it's not restricted to 2D. So it's just our computation and can be extended to 3D in a straightforward manner. Actually.
I hope the answer was good for Manoj. I think okay, yes.
So thanks.
And maybe let me ask a last question. I mean, in this, you said that here you have let's say what you call low contrast, meaning yes. Like the white and sorry, not the black parts have a very small difference. Yes. What's about just eliminating the white, the black, sorry, here, and just having something continuous with holes? Would this approach work as well?
You mean like a continuous variation of the parameters?
Yes, just one parameter, but no, sorry. It means I just mean one single material with holes. So then you have this infinite contrast, in fact, because one is a vacuum.
Well, so infinite contrast, it poses a number of problems in the method we use right now. The rate of convergence in the solver, in the forward solver, depends on the contrast. So it will still converge, but much more slowly. And if we have high contrast and then so resonances in the medium, the topological derivative step has to be adapted because you will need to work on to evaluate the topological derivative, the topological sensitivity of some eigenvalue problems, and that's so we did not do that in this work. So that for us that has to be done. I know that some authors have worked on that. There are a couple of works on that in the literature.
Okay,
but for sure that will enhance the effects. So that's definitely the things that must be looked into.
Yeah, because I think, I mean, from the side of the talk, I think it would be very interesting to have this case, I mean, especially for the, let's say, application aspects, because very often you just have one material and you make a structuration of one material.
Absolutely.
And just by curiosity, I mean, in this extreme materials, for example, when you look at this auxetics or dilational stuff that Milton was proposing, mm-hmm. to approach like the isotropic materials with the Poisson's ratio converging to -1, for example, I'm not sure one could, I mean, even if you would try to optimize this, that without getting like this infinite contrast, you would manage to get a result.
Yeah, and absolutely, and we have worked with a Pierre Sepécher also that you might know on the optimization of trusses. So if you consider a truss, because you want to construct some sort of pantographic structures, so you have void and a material. Basically, you have some ligaments that you can oriented and with which you can connect some nodes. There are some options. It's almost as if you were doing some sort of it's a combinatory problems where you have a set of nodes and you're asking yourself how you can connect this set of nodes by a bar or not. So it's a different types of optimization that must be used.
Okay, thanks for the reply. So do we have any other question from the audience? If not, let me thank Cédric once again. It was a very nice presentation. It was recorded and it will be online in the coming hours.
All right, thank you very much.
Thank you very much, Cédric.
Thanks for the discussion.
Thanks and talk to you soon.
Bye-bye.
Bye.